Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Today we'll show different types of boundary conditions on a single application in computational fluid dynamics, and we'll see the differences. Okay, so let us start the first application. This is a cylindrical tank. Actually, it is having two open entries. At the bottom also we are having one open entry, and the top also we are having another open entry. Half part of this one is filled up with water, and the top part of this one is filled up with air. Initially, we will apply one boundary condition such that from the bottom part, liquid will be forcing out at a specific velocity and direction of gravity will be upwards. Because of that, air will be moving upward direction and liquid will be passing from this entry to downward direction. And in the second analysis, the direction of gravity will be downward, and both the down entry and the top exit should be exposed to atmospheric conditions. Okay, we are starting the simulation from here, and the simulation environment will be initiated with wizard itself. Default name of the project we are keeping as project 3. Next to that, the unit system will consider as SI, and the default parameters we are considering, we are not changing anything. Next to that, it will be an internal analysis, and it is a time dependent phenomenon, so it will be transient analysis. We are considering total time for analysis will be 8 seconds, and output time step should be 0.1 seconds. And definitely gravity will be involved, and in the first case we will consider that gravity will be in the upward direction, so it will be plus 9.81 in the y direction, and along z component it will be 0 meter per second square. As it is a free surface technique, so we have to tick free surface. Next to that, gases we have to consider. Default gas will be air, and liquid will be water. As it is a free surface technique, both the fluids will be there as an immiscible fluid. Next to that, as walls are not that much of important in this case, so default wall thermal conditions or roughness we are considering. Next to that, initial concentration will be air. Let us finish this. This is a computational domain. Initially, what we have to do is the bottom part of this one we have to fill up with water, and that can be done from the initial conditions. And let us select that bottom part of this container. From the solid bodies we can select it. This is the bottom part. Let us disable this one as solid, and we want to define this one as water. Selected. Now we can hide our computational domain. Next to that, we have to apply our boundary conditions. Initially, we want to apply only one boundary condition. That means from the down part, water will be moving at a specific velocity. So boundary conditions, insert boundary conditions. We are planning to have the water velocity to be 10 meter per second in the downward direction, and substance concentration it will be definitely water. Let us select that opening. We can rotate a little bit for proper selection. Select other face of extrude boss base 2. Selected. Next to that, we have to select some goals. We have to have two goals, that means volume fraction of water and air separately. That will be as global goal. Insert global goals. We want to select volume fraction of water and air. Average volume fraction of water and air we are selecting. When check. Now the goals are defined. As it is a transient analysis, you have to set up some conditions. It will come from input data. Let us select calculation control options, and from here, from settings, we have to select periodic iterations, and we want to set up some different parameters. It will be obtained from here. We want immiscible air and immiscible water. By the same time, we want to have volume fraction of water and air. Okay, done. Next to that, we want to run this simulation. Let us run it. With a new calculation, let us run it. You see some kind of immiscible layer of water and air is visible in the solar window. We have initiated this simulation for 8 seconds, and we have to get the results up to each 0.1 second. You can see heterogeneous mixing of water and air inside this container. Let the iterations move on. Whenever it is finished, we'll see the different cut plots from the results. Okay, we can see the solver is finished. Now we'll see the results from the different cut plots. Let us close this. Results, and we want to see cut plots from front plane. Insert cut plots, and you want to see volume fraction of air, or we can see volume fraction of water also. Anyone we can check. Let us see volume fraction of air. Let's check. By the same time, we want to make the transient explorer on. Now let us run this one and see how the volume fraction of air is changing. Within 8 seconds, we can see the volume fraction changing. From the down parts, actually, water is coming down, and again same time air is entering from the bottom part. Let us clear and hide these things. We want to see something else. Now we'll see the surface plots also. Let us clear this cut plot 1. Next to that, we want to see the surface plots. Insert surface plots, and we want to use all the faces, and we want to see volume fraction of air. Later on, we want to see these results in the form of XY plots. That means across the height, how this fraction is changing. That one also we'll see. Let us clear and hide these things. Next to that, we want to see isosurface. That means it will be the separation layer in between the water and air particles. Let us select isosurface, and it will show how the layer is changing or moving, as it is a time dependent phenomena. At different times, that immiscible layer of water and air will be moving from place to place. Let us clear and hide these things. ISO surface 1, clear and hide. Next to that, we want to see our XY plot, that means as height is changing, how the fraction will change also. That one you can see from XY plots. XY plots, insert, and we can have a lot of things, but our main aim is to see the volume fraction of air or water. We're going to see both of them. Let us see from here. We have to select that line. Let us show. You can see the volume fraction of air and water separately. First one is volume fraction of air. As height is changing, volume fraction of air is also changing, right? Let us see this one from here. How this volume fraction of air and water is changing. At different times, you can see at each second it has come to the end. At a different height, you can see the volume fraction of water and air separately. We can transport this data to Excel also for have a better representation. Let us transport this one to Excel. We have to transfer this data to Excel. This is the volume fraction of water. Some kind of turbulent mixing was there inside this container, right? Next to that, we will see the volume fraction of air. We can have different types of things. For volume fraction of water and air, it is completely reverse one. Okay. Next to that, we want to apply some different analysis with different boundary conditions with the same model, right? So let us clear this transient explorer and we want to initiate another analysis. For initiation, what we'll do is we have to change the boundary conditions only. So for ease of simulation, we'll copy this analysis as a clone and change the required boundary conditions accordingly. Let us clone it to project number 4. This is project number 4. Now we'll change the boundary conditions as per our requirement. Let us delete the previous boundary conditions. And also in this case, the direction of gravity should be changed. We want to apply only atmospheric conditions at the entry and exit locations. And because of gravity, water will be falling down only, right? So we have to change the conditions. That will be often from general settings. And we can change the gravity direction. It will be along direction Y and it will be minus 9.81 meter per second square along downward direction. Applied. Okay. Next to that, we have to apply boundary conditions at the entry and exit locations. It will be atmospheric pressure. So boundary conditions, insert boundary condition. It will be atmospheric pressure or environmental pressure at the both the locations. Rotate view. Select other. Face of extrude boss base 2 selected. Go and check. Now let's try to understand when direction of gravity is downward, because of gravity effect, water will be falling down, right? If we don't apply any kind of boundary condition at the top end, then we cannot see the volume fraction of water will change. In the next one, we have to apply boundary conditions at the top exit. That means it will be exposed to atmospheric condition. And that means we want air to be increased from here. Boundary conditions, insert boundary condition. It will be environmental pressure or atmospheric pressure from the top entry. Rotate view. Select other. Face of extrude boss base 1 is selected. Go and check. Next one, we have to start with the input data, and we have to select calculation control options, and as determined before, we have to select those conditions. That means we want to have immiscible water and immiscible air, by the same time volume fraction of water and air to be checked in. Okay, done. Now we can run this simulation with new calculations. Let us run it. Solve window has already started iterations. We can see the results from here. See, as it is a transient analysis, so as time is increasing, the volume fraction of water is decreasing. Let's say down part is water and top part is filled with air. So at different times the fraction will change. Let the iterations move on. The solver is finished. Now we see the results from the cut plots. Results. We want to see the cut plots. Insert cut plots, and we want to see volume fraction of air. As it will be increasing, and we want to see from front plane. Let the transient explorer be on. Is on, and let us run it. You can see at different times the volume fraction of water is decreasing. Similarly, volume fraction of air is increasing, right? From this analysis, we can go for some kind of optimization. Time depending constant. If we change the input variables, maybe the input diameter, at what diameter the volume fraction of water will be 0 and volume fraction of air will be 100%. Okay. Now here you can see one thing, like as the top part is exposed to atmospheric condition, volume fraction of air is increasing, and as water is coming down, volume fraction of water is decreasing. Okay, this is volume fraction of water at different times. It is decreasing definitely, and that of air is increasing. Next to that, we want to see surface plots. So we'll clear and hide these things. Let us clear cut plot 1, and next to that we want to see surface plots. Insert surface plots, and we want to see the results from all phases. It will be volume fraction of air. Green check. Let us play. So water is coming down and air is being filled up from the top entry. Okay, let us close it and clear and hide these surface plots. Next to that, we want to see our isosurfaces, that is the interface between liquid, water and air. Insert isosurface, and we want to see volume fraction of air. We will check. You will see how the immiscible layer of water and air will be moving up and down. Let us play this. You see the surface is coming down. It is the interface between water and air. That layer is coming down at different time intervals. Let us clear and hide these things. Isosurface 2 should be cleared and hidden. Next to that, we will see XY plots with different heights. We'll see how the fraction of water and air is varying. We will see volume fraction of water and air separately. Let us select that line, and we can see it from here, and we can export this to Excel also. Let us see from here. And you can see how the layer of water and air is also varying, right? It is completely reversed one. As the percentage of water is decreasing, percentage of air is also increasing, right? Let us export this data to Excel and analyze again. XY plot, edit definition. Let us export to Excel, and you can see first one is the volume fraction of water. When the height was 0, the initial volume of water was 65%, and when the height is changing, you can see at 0.2 meter height, the volume fraction of water has come down to 0. After that, it is maintained 0. That means the volume fraction of water has come down to 0 within a very short time. Next one, you can see the volume fraction of air. It is completely reverse compared to the volume fraction of water. Initially, volume fraction of air was near about 30%, and when the length was 0.15, then we got the volume fraction of air as 100%, right? So from this analysis, we could understand with the variation of boundary conditions how the results are varying. Not only that, by changing the direction of gravity also we're getting different types of results. So while applying boundary conditions in CFD analysis, we have to be very accurate about our boundary conditions, right? So this is all about our today's video. Thank you for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.